Welcome back, everybody. This is our video solution to problem 13 from the Fall 2020 Math 210 final. And this question is all about sequences. We want to know whether or not these sequences converge, and if they do converge, what do they converge to? So let's jump into A. So in A, we're given a sequence whose terms are, well, almost rational functions of n. There is this square root in here, and it makes things a little bit weirder, but ultimately, the intuition needs to be when I have sequences whose terms are of this form, look for the highest powers of n. Okay, so look for the highest powers of n in the numerator and the denominator. And in this case, you see we have a power of n, which is a 2, and then you have a 1 and a constant. Then on the bottom, you have a 2. Square root of n looks like it's not a power of n, but of course we know that the square root of n can be written as n to the 1/2 power. So this is really a 1/2, and then you again have a constant. So the highest powers of n are sitting here right at the beginning. All right? And when you find those highest powers, you more or less just ignore all the stuff that comes after those highest powers. All right? If they're written in a different order, of course, then you wouldn't say after, right? You just, okay, just ignore everything. But now, in this case, they both have the exact same power. And so I would cancel these n squareds and say, oh, look, I'm just left with 1/5. And that's actually what this sequence converges to. All right, we can make this precise. All right, so if we look at n squared minus n plus 1 over 5n squared plus the square root of n plus pi, and I divide out a copy of n squared from both the top and the bottom. So I'll get here n squared times 1 minus 1 over n plus 1 over n squared. Over, again, dividing out an n squared, I'll have 5 plus, now I'm going to think of this root n as an n to the 1/2. And so when I get rid of an n squared, this becomes n to the negative 3/2, or 1 over, n to the 3/2 power. And then plus pi over n squared. Okay, and you can just distribute the n squared back in to make sure that we're really getting the correct original expression. Now we know that n is not going to be 0 in the long run, so we can cancel these n squareds, and I'm left with 1 minus 1 over n plus 1 over n squared over 5 plus 1 over n to the 3/2 power plus 5 over n squared. And the key here is that we can see as n goes to infinity, 1 over n goes to 0, 1 over n squared goes to 0, 1 over n to the 3/2 goes to 0, and pi over n squared goes to 0. So the only thing left over as n goes to infinity is this 1 and this 5. And therefore, this thing as n goes to infinity goes to 1 over 5. Okay, and therefore, A bar converges to 1/5. All right, now let's look at B. So you have two pieces here, right? You have the sign of n on top and you have n on the bottom. And one of the most common mistakes here is somebody looks at the sign of n and they say, oh, first they might think, oh, that's an alternator. It goes between -1 and 1. Well, I mean, sort of. The range is lying between -1 and 1, and it does sort of oscillate back and forth. And so then somebody might say, you see, it can't converge because it just keeps oscillating. But what's happening on the bottom? What's happening on the bottom is that n is going to infinity, which means if I just looked at 1 over n, that would be going to 0. So I have this sign of n, which is oscillating somewhere between -1 and 1, and you're multiplying that by an expression, 1 over n, which is going to 0. So here's how we can resolve this. We know that -1 is less than or equal to sine of n, is less than or equal to 1. And if I divide by n everywhere, then I actually get my sine of n over n in the middle, and it's bounded between -1 over n and 1 over n. And -1 over n, this goes to 0 as n goes to infinity, and 1 over n goes to 0. But that means that sine of n over n, which lies in between these two expressions, which both go to 0, must also, by the squeeze theorem, go to 0. And so we conclude that b bar converges to 0. All right, now we go to C. And C is the most complicated looking of these because it's actually a series in disguise. Okay, remember a series is really just what we call a sum sequence. Right? Series is the limit of a sum sequence. Right? There's an underlying sequence here, right? That would look like 1/4, 1/9, 1/16, 1/25. And you're adding the terms, right? So I start with 1/4, fine. Then you add 1/4 and 1/9. Then you add the first 3. Then you add the first 4. So this C is a sum sequence, which means that its limit is the series. Okay, its limit is a series. Well, what is it we're actually looking at? Well, we're looking at the reciprocals of, these are squares, right? 1/4, that's 1/2 squared. And 1/9 is 1/3 squared. And 1/16 is 1/4 squared. And 1/25 is 1/5 squared. Now, this is a series that we actually have worked with extensively this semester. So we'll write down one which is not quite right, which is if you start at 1, and you do 1/k squared. This is actually what we call the Basel problem, and we knew that this converged to pi squared over 6. Now, we're missing a term here, right? This one would start at 1/1, not 1/4. Well, that's easy enough to fix. Let's just pull out the k equals 1 term. So 1 plus, now we can start at 2. Okay, and this would still equal pi squared over 6. So now if I want just the series that starts at 2, I'll just subtract 1 from both sides. And I'll get that the series starting at 2, 1/k squared is equal to pi squared over 6 minus 1. And therefore, C bar converges. Well, they all converged, but C bar converges to pi squared over 6 minus 1.